All right, so what I'm actually going to do is I'm recording this just because I don't want to re-lecture it. Okay, so today is activity 3.7, restriction digest and gel electrophoresis. And today, the really important part is understanding how restriction enzymes work. They just cut DNA, and then why we use that with gel electrophoresis, which is the gel thing we were doing last time. Remember, like, well, you don't remember, Jenna, but you know, like everyone else. Just kidding.
I wasn't here.
That was also Savannah and Andrew were absent. Okay, so we're moving on to
I wasn't here either.
this part. Oh yeah, it's okay. I'll catch you guys up. After school club. After school.
Thanks.
Yeah. So today we're going to go over something called palindromic sequences, restriction enzymes, and the big picture of what we're doing today. So we're going to jump right into palindromic sequences. Do you guys, don't even look here. Do you guys know what a palindrome is? Like first grade. I'll give you an example. Ready? Mom is a palindrome. Okay. Dad is also a palindrome. Hannah, with an H on the end, is also a palindrome. Race car is also a palindrome. Can you guys figure out what a palindrome is now? When the front meets the back, right? It's the same way of reading it, multi-direction. So if you read it this way, it's race car. If you read it this way, it's race car. These are palindromes, and they're, oh, don't cancel. And the reason why palindromes are extremely important is because that's what restriction enzymes are going to actually recognize. So ready? Get ready for this. Ready?
Ready.
From what I'm about to show you, try to guess where in this sequence right here the palindrome is, okay? And guess what it is. Ready? Ready? Oh. So if a restriction enzyme met this DNA fragment, had the pleasure of meeting this DNA fragment, this is what would happen. It would break apart at this line right here. So notice where it broke apart. What do you notice? What do you notice? Okay, I'm gonna give you the next one. Ready? Try to see the next one. Okay, look right here. Try to guess what's the palindromic. Ready? Even predict where it's going to split, maybe. Oh. Okay. All right, let's go one more time. Let's go to another. Oh, whoops. Nope, that's the answer. Ah! Okay. So look back here. Right? Look at where it splits. Look at the letters where it splits. Do you see what's happening? Ah. Okay, what about the next one? Do you see the pattern? Okay, let me make it more explicit. Look right here. What do you notice about these sequences right here?
Backwards on the lower row.
Yeah, let's read it together this way. So if you read it here, like this, it's G-A-A-T-T-C, right? But if you read it this way, it's also G-A-A-T-T-C. It reads the same this way and this way, right? They read the same. So it's not exactly like a palindrome in that there's only one sentence. It's actually two sentences that are flipped over. Weird. Okay, so if you look at the next one, this is the same one we did before. Notice how right here it's going G-A-T-C this way, and this way what is it doing? Oh my gosh, palindrome! And the cool part is there's restriction enzymes that are present in bacteria. And today you're going to kind of try to understand why they're found in bacteria. Viruses. Viruses. And what happens is these enzymes, EcoR1, BAMH1, TAC1, and ALU1, these are all restriction enzymes that will cut specific recognition sequences. So on your DNA strand, if you saw this on your DNA strand, EcoR1 is going to go to town on that. And it's actually going to cut it in this very unique band pattern like this. It actually starts cutting right after the first letter G, and it cuts right after the first letter G here, and then it like divides it this way. Do you see how it's splitting up like that? BAMH1 is going to do the same thing. It's going to recognize these sequences and split it up like this. And then TAC1 is going to recognize this sequence and split it up like this. And then Arthrobacter luteus, which actually isn't very common, is actually going to specially just cut it right in the middle. So all of these three, are going to cut it in this weird like, I don't know, stair pattern, but this is the only one that cuts straight. And this is actually called a blunt end, and these are all called sticky ends, but don't worry, because you'll cover that while you do the actual activity. Okay? So, the big picture is what's really important for today, and this is what I would like you guys to take notes on, like why we're doing everything. It's going to be a series of drawings / writing, so just bear with me, okay? Bear with me. All right, here we go. So the whole purpose of DNA fingerprinting is to find what your DNA fingerprint looks like. Okay, so I need to sit down for this. I'm going to sit here. Okay. All right, so let's pretend you don't have to draw this. I'll tell you what to draw. Let's pretend you are at the crime scene. You're like, ah. And I'll give this person glasses, so now it's Eileen. Okay, isn't that beautiful? So Eileen is looking at the crime scene, and there's like blood everywhere, but she notices in the blood, there's a clue. So what she's going to do is she's going to get a cotton swab. That's my cotton swab. And she's actually going to swab DNA, or the blood, for DNA samples. So what you should actually draw here is this. At crime scene, yes, we will, I know, my writing's horrible.
Can you zoom in on that?
Swab, I can. I'm lazy. For DNA. So during the actual crime scene, which is next week, on Tuesday you will actually encounter the crime scene, someone will be dead. You're actually going to get Q-tips and swab a bunch of places and hope that you get some DNA somewhere, okay? So swab the murder weapon, swab the person's cheek, swab everything, okay? So you're going to swab for DNA to get your crime scene DNA. So this right here is my cotton swab, and then this right here, DNA, swabbed. Yeah. You don't have to draw the faces. I'm just waiting. You don't have to draw the faces. I'm just waiting. Okay, here we go. So from here, after you swab the DNA, the next step is to actually... Oh, hold up one sec.
Can I draw there? I know. I have ears. You have a stylus?
I'm just doing it.
He just took it.
Just do it. Just do it.
This will be posted on Emoto, so you can just watch the recording. All right.
It's going to be the longest recording ever.
This is going to be super long. Here we go. So after we swab our DNA, woohoo! We're actually going to have to amplify the DNA. So we have to amplify the DNA via PCR to make sure we have a lot of DNA to work with. Because the fact of the matter is you might actually get a small sample of DNA and just very little of that DNA. You might only have like a few cells worth of DNA. Sorry, I know it's blocked by Deseri desktop trial. It says amplify DNA via PCR to make sure we have a lot of DNA to work with. One more time, it's amplify DNA via PCR to make sure we have a lot of DNA to work with. Amplify DNA via PCR to make sure we have a lot of DNA to work with. Okay. From here, our next step, our next step is going to be cut the DNA with a restriction enzyme. Okay, cut the DNA with a restriction enzyme. And this is where the most important part is, because this is where you start getting the key things that you need to put into the gel electrophoresis chamber later. Okay, so we're going to actually keep continuing with this. Okay, and just for completion's sake, I'm going to go to the next step but explain it afterwards, and that is run the DNA fragments in a gel electrophoresis chamber, or you could just write in a gel. So run the DNA fragments in a gel, and that's the same gel that you guys were playing with on Tuesday, where you injected the dye into the wells. And so we'll go over why that's important. And today you're going to learn how to read crime scene DNA photos. Good stuff.
Is it
I smell some pizza.
Yeah.
Okay. All right, so this is the real deal now. I want to ask you guys a question first. Do we have the exact same DNA?
No. Nope.
No. Everyone's DNA is very unique to them, right? That's your blueprint of life. So, answer me this query. If I have person one... Oh, stop.
I'm sorry.
Why are you saying sorry?
Oh, I didn't think so. The table.
Oh, you're good. Oh. Confused. Why?
And you said it's Italian food.
I know, it's distracting me.
Wait, so it's not you?
No. I don't understand why it's doing that. Ah, why is it doing that? Okay, sorry guys, I don't know why my thing is not working. I'm gonna have to just write super tiny. Okay, we're gonna continue. Here we go. I'm just gonna start here. Oh. It's just completely like out of whack. Oh, okay. Alright, sorry. I don't know what happened, but we're just gonna go like this. Okay, so we have different DNA strands, right? I know, sorry. This is what we have to do. Deal with it. Okay, shh, guys. Hello. Hi. Okay, so if I have two different people, right? So let's say I have like Amar right here and Wells right here. Okay? Are they going to have the exact same DNA? No, right? Like Amar's going to have like G, 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 C, C, T, A, T somewhere. G, A, T, C, A. Right? And then obviously the double strand right here. G, G, A, T, A, C, T, A, G, T. And then Wells is going to have, Wells is going to have slightly different DNA. TC, G, G, C, A, T, C, C, G, C, C, T, A, G, C, C, G, T, A, G. Okay, so notice how like Obviously, you would have like way more than this, like 3 billion base pairs, but we're just going to do like 12 because I don't want to draw out 3 billion. If you look at this right here, where in a Mars DNA do you see a palindromic sequence? Which base do you see a palindromic sequence? Hint, look towards the end. So do you see it right here? TGATCA. TGATCA right here. So if I submitted his DNA to a restriction enzyme, it would actually cut like this, and it would make this DNA fragment and this very, very small tiny DNA fragment here. So he would have one long DNA piece and one little tiny DNA piece right here. If I cut Wells' DNA, where would I cut? Where do you see the palindromic sequence? Right here. You have GATC here, and so his DNA would cut like so. Okay, and so he would have one kind of small DNA piece and one kind of big DNA, so he'll have something that looks like this. Right? And so because you have differently sized fragments, what's going to happen next is we can load the different sized fragments into these wells. So let's say we put a Mars like big piece and small piece here, and we put Wells kind of medium piece and slightly bigger medium piece in here. If we run a current through it so that the negative charge to positive charge, do you guys remember from Tuesday what charge DNA is? It's negative charge, right? So DNA is going to want to go this way, and the smaller DNA pieces are going to go further. So a Mars really small piece is going to go all the way down here, and then his like slightly big piece is going to stay pretty close because it's too big to go far. And Wells is going to go kind of medium. Both of them are about the same size, so they're going to go the same distance. Okay? So, really quick. Amar, can you tell me, based on this right here, if I cut your DNA strand and like Adelina's DNA strand, would you guys have the exact same fragments?
No.
Okay? And let's imagine, Adelina, let's imagine you have a fragment that's this and this. And then, Jenna, let's imagine that you have two mid-sized fragments. Which of you two do you think are going to see a band pattern further beyond the wells? So if this is Adelina and this is Jenna, who is going to show a DNA pattern that's further away from the wells? Adelina, because she has a smaller DNA fragment, and that's going to travel further down the line. Okay? So that's basically how we can do it. And we can actually do this to the extent where you'll have about 100 band patterns, and you can match all 100 band patterns for different perspectives, and to see basically whose DNA matches a DNA you found at a crime scene or something. Okay? So the basic idea of this entire kind of activity is that we're going to take people's DNA, we're going to cut it up with the same enzyme so that they make different sized fragments, and then we're going to run it through a gel so that we can see your specific band pattern. So every single person in the world, if I gave you this right here, every single person in the world would have a different band pattern. So if I took all 35 of us and kind of just like plotted out our DNA, so this was like Jenna, this was Adelina, this was like Jocelyn, right? You guys would all have slightly different band patterns because your DNA is just a little bit different. And then we can eventually match that to a DNA we found at a crime scene and be like, oh yeah, it was definitely Jocelyn because her DNA pattern matches exactly what the crime scene had. And what's even cooler is your mom and dad, right, gave you half your DNA each. So we can actually even track paternity-wise. If you have half the bands of like one person's DNA, you are most likely their child because you took half their DNA from them. Yeah. So you can actually do this as a paternity test too. Okay. Or a maternity test. But usually it's pretty obvious where you were born out of because there's a person giving birth to you. Okay, we're done with that. All right, so